right, I want to go over a problem today on one-dimensional kinematics, and I'm going to show you how to solve it using the problem-solving strategy that we've been talking about in this class. This is a little more complex of a problem because it involves two different phases. So there's a first phase and a second phase. So it's a step more complex than the stuff we've been talking about, which is why I want to go through one of the problems today and show you how we're going to solve one of these. So the problem we have is a test rocket is fired straight up from rest with an acceleration of 20 meters per second squared. After 4 seconds, the engine burns out and the rocket coasts upward and then falls to the ground. What is the maximum height of the rocket? So there's our question. Now every time we solve a problem, first step, draw a picture. So my beautiful art skills here. Here's my rocket. We start on the ground and then we have thrust for 4 seconds, and then we stop with the rocket thrust and it goes up till its maximum height. Oh, there's nothing there. Here's our maximum height. We want to know how high that is. And then it's going to fall down, but in this case we don't really care what's happening after we get that maximum height. So there's our basic picture. Doesn't matter how good a drawer you are, you can see. And the two things we should add on our picture, we need to pick our origin. So I'm going to set my origin to be the ground. That's where we start. And we also need to choose a coordinate system. Typically, we choose up to be positive. You can choose a different one, but I like up as positive. That's our standard. And if you always choose the same one, you don't have to worry about any changes, anything. It's just be, oh, up is always positive. So there's our first step. Draw a picture. Get our coordinate system, get our origin. The next step that we do is we figure out what do we know. So the way we do this in kinematics, typically, we do a little chart. And the 6 kinematic variables we work with, initial position, initial velocity, final velocity, acceleration, and time. So we've got these 6 variables. Let's see what we know based on the problem. Well, the rocket starts on the ground, so I'm going to say my initial position is 0. That's what I chose right here. We know it starts at rest, so my initial velocity is 0. What else do we know? Well, do we know what its final position is? Nope. Okay, that's a blank. Do we know what its final velocity is? Well, at its maximum, it is not moving at the maximum height. So this is a tricky part. Remember, this is something you know. We know that at its maximum height, the velocity is 0. And do we know anything about acceleration? Yes. So it was 20 meters per second squared for 4 seconds. And then it was free fall, and that's where I stop. And I say, uh-oh, this is a two-phase problem. This right here, this acceleration, anytime we use our kinematics variables, this has to be a constant. Because the kinematic equations we use only work if we have a constant acceleration. Do we have a constant acceleration here? Nope. We have an upwards acceleration for phase 1. And that's from here to here. And then from here to here, phase 2, we're not thrusting upwards. We have gravity pulling downwards on us. So we have a separate acceleration. This means I can't do this in one chart like we've been doing before. So what do? Well, we do a second chart. All right, so I need 2 charts. That means I need to start over again. Uh-oh. I need a chart for phase 1 and a chart for phase 2. So I'm going to have 2 charts. Same 6 variables. We don't have to worry about changing anything there. All right, so there's our variables. And I'm going to choose this one as phase 1 when we're accelerating upward, and phase 2 when the rocket thruster no longer there. So now I got to be a little more careful because the data that I have to decide where it's going in my chart. All right, so phase 1, from here to here. Is x initial still 0? Yeah, because we still start at the ground. How high does it go in phase 1? Don't know. That's a blank. It's okay. We can have blanks in our chart. That's okay. Is the initial velocity 0? Yeah, we're still starting on the ground. Okay. V final. The final velocity. That's how fast it's going right here. Don't know that. Again, it's a blank. It's okay. Blanks are okay. Acceleration. And here's our tricky part. What's the acceleration for phase 1? This is the upwards acceleration. So I'm going to have a positive 20 meters per second here. And we know this phase lasts for 4 seconds. All right, 2 blanks, well, we'll see if we've got it. So now let's go to phase 2. So we have phase 2 when the rockets stop here, and then it's going to slow as it goes all the way to the top. So what's its initial position? So the initial position for this one is its position right there. We don't know that. We don't know that. But if you think about it, this one is the same as that one. Its final position in phase 1, where it ends, is where it starts in phase 2. So these two are the same. So that might be useful. Final position, way up here. That's what I'm looking for. So this is my target variable. That's what I want. Initial velocity, how fast is it going when the rockets turn off? Don't know. How fast is it going at the end? And again, I know that. It is stopped. So V final is going to be 0. What's the acceleration when it's going from here to here? So the rockets are done. You might want to say initially, you might say, well, there's no acceleration. Well, if there's no acceleration, that means the velocity isn't changing. What would the motion of this thing be? The motion would be constant velocity. Whatever it was doing, whatever speed it was doing, it would just keep doing that speed. It's not a constant velocity, so it's not 0 acceleration. What is the acceleration? Well, okay. Do we know it? What's causing it to slow down as it goes up? Gravity. It's the acceleration due to gravity. So we do know the acceleration in phase 2. Negative, remember that negative sign, negative 9.8 meters per second squared. All right, so it's accelerating due to gravity. Gravity's pulling downward on it. We got that negative. Do we know how much time it takes to go from here to here? Nope. Okay, so what do we have? We have a lot of blanks, and we're looking for this. This is what we're looking for. So we've got our picture, we've got our coordinate system, and our origin. We have our knowns, and our unknowns. Our target is right here, our final position. At this point, we start saying, how can I get the thing that I want? So I'm going to say, to get x final, we have 3 equations that we can use. We've got x initial, x final equals x initial plus v initial t plus 1/2 at squared. All right, that's got x final in it. We have v final equals v initial plus at. That's not going to work. It doesn't even have the thing we want. And we've got v final squared equals v initial squared plus 2 times the acceleration times the change in position. You might look at that and say it's not got x final, but it does. Remember, this is the change in position, so it's the difference between these two. So would this one work? Maybe. Would this one work? Maybe. Let's see what other information we have. So we're looking for x final. So here's my question mark. I want that. Do I know x initial? No. Do I know v initial? No. Do I know time? No. This isn't looking good. Half. I know half. I know my acceleration. Okay, I don't think this is going to work. I don't think it's going to work right now because we don't have enough information. Maybe this one? Do we know v final? Yes. Okay, I got that one. Do we know v initial? No. 2, I know 2. I know the acceleration. And, well, I don't really know x, delta x, do I? Because delta x is x final minus x initial. It's the change in the position. This is what I want, but I don't know my initial. Okay, so at this point it looks like all of them don't work. What do we do? Well, we have to use one of these and figure out from phase 1, I'm guessing, some of these things that we need. I'm going to go back to this one, because this one, the only things I needed to solve this equation were v initial and x initial. Let's go back to our chart. X initial, I know something about x initial. The initial position for phase 2 was the same as the final position for phase 1. Can you guess what I'm going to do next? What's the initial velocity of phase 2? Well, yep, it's going to be the same as the final velocity of phase 1. And so we can get this useful information. We can get v initial. We can get x initial from this information. So, well, I hope we can at least. Let's see. Now, you might say, why didn't I pick one of the other ones? You know, this one doesn't have anything that we are looking for, so that's number 2, not going to work. Why didn't I choose this one? Well, maybe I could have. What would I need? I'd need exponential again. And here I'd need my time. I doubt I have enough information to get the time out of that. I probably could, but I think it'll be a lot more work. We can try it later if you want. For now, I'm going to focus on this equation right here. So I'm going to use this equation, but I need v initial and I need x initial. So I'm going to put these two in. Once I have these two, I can use this equation to get the thing that we're looking for. We're looking for that final position, the maximum height. Okay, erasing. So we are going to try to figure out what v initial is and what x initial is. And we know these are the same as the finals from phase 1, excuse me. So how can I get x final from phase 1? So this is the same as x final from phase 1. This is the same as v final from phase 1. I need x final in phase 1. Okay, same three equations? I'm going to try this one first, just to see. This is one I tend to start with. If that doesn't work, I go to the other ones. X final in phase 1 is x initial in phase 1 plus v initial in phase 1, t, 1/2 a, 1, t squared. I think I've got this. This is what I'm looking for. I know x initial, I know v initial, I know my time, I know 1/2, I know a, and I know my time. Got it. This will get me what I need. This will get me my x final. Okay, one of the things I like to do when I'm looking at the math here is I like to get rid of all the things that are 0 because that makes it a lot cleaner and easier to see. Anything 0? Well, x initial is 0. That whole term drops out. V initial is 0. That whole term drops out. Okay, this set comes down to something a lot easier, much simpler. 1/2 at squared. Okay. 1/2. My acceleration is 20 meters per second squared. My time, 4 seconds. And don't forget to square that. So x final in the first phase is, well, half of 20 is 10, times 4 squared is 16. That's going to be 160. And now the units, let's see, I've got a meters left. The second squared here and the second squared here cancel. I'm left with a meters, which is right. It's position. We want meters. So x final one is 160 meters. Let's pop that in. I now know this, which means I now know this. Great. Maybe we can do the same thing to figure out our v final. So we need to know what our v final is. Let's erase. All right, now we're looking for v final in phase 1. Okay, v final. So my first equation, the one I just used to figure out the position, doesn't even have v final. What are my other two equations? V final equals v initial plus at. Ooh, that looks promising. The other is v final squared equals v initial squared plus 2 times a times the change in position. Also promising. All right, can I use this one? I'm looking for v final. Do I know my v initial? Yep. Do I know my acceleration? Yep. Do I know my time? Yep. Okay, this one will work. With the other one. V final is what I'm looking for. I know v initial, I know 2, I know a. Do I know delta x? Initially I didn't, but I just figured out x final. I could use this one. They'll both give you the same answer. Doesn't matter which one you use. If the squares bother you, if the squares say, oh, that's too much work, use the simpler one. I like the simpler one. So I'm not going to use that one. I'm going to use the easy one. Anything 0. Well, v initial is 0, so I can drop that out. I'm just going to be left with v final is equal to acceleration times time. Well, that's pretty easy, isn't it? I think we can do this one in our heads. 20 meters per second squared times the time, 4 seconds. I end up with a v final of 80. And let's see, meters still on top. One of these cancels with that one. Meters per second, that's the right unit for velocity. All right, so 80 meters per second, which means that pops over here, 80 meters per second. That's really fast, by the way. So, but yeah, it's a rocket in 4 seconds. I mean, 1, 1,000, 2, 1,000. If you've done rockets, you know that's a really long burn phase. So we're almost there. We're almost there. We are now ready to take our last step to figure out what this is and actually answer the question. More erasing. All right, last step. Now this was the equation we'd chosen. V final squared equals V initial squared plus 2 times the acceleration times the change in x. And looking at my chart, I don't know my time. This is the only equation that doesn't have time. So whenever you don't know time, try this one. Anything 0? Well, v final is 0. Okay, we can drop that out. Nothing else is 0. Okay, so 0 equals v initial squared plus 2 times the acceleration times the change in position. We know v initial, we know 2, we know acceleration, and this is kind of what we're looking for. How far does it go? What's the change in position? Because once we know where it started and we know the change, we can figure out x final. All right, so I'm going to bring this v initial squared over to the other side. Negative v initial squared equals 2a delta x. I'm looking for this, remember. I'm going to divide both sides by 2a. So negative v initial squared over 2a equals delta x. All right. Now that negative sign might worry me. I look at that and I say, I'm not sure about this. Because if I have a negative delta x, what would that mean? A negative change in position. That would mean it dropped. And we want our max height, so that might worry me. Let's see what happens when I put my numbers in. I've got a negative. V initial is 80 squared, negative 80 meters per second squared over 2 times my acceleration. Now it's not 20. Remember to use the correct acceleration. Negative 9.8 meters per second squared. Haha, negative, negative. They cancel. So my delta x is going to be negative 80 squared. I'm just going to get rid of those. Okay, no more negatives. 80 squared over 2 times 9.8. And when we do that in the calculator, let's see what I got. Hopefully you'll get the same thing. I ended up with a delta x of 326 meters. So delta x, that's the change in position. So it actually changed, and this is positive, so it went upwards, because way back here, we picked positive as up. It went up 326 meters in this phase, just in this phase. So if it started at 160 and it went up another 326, we know our final position, our maximum height, is 326 plus 160. You can do that in your head. You can do it. So 6, and last, and 2 plus 6 is 8. 3 plus 1 is 4, 486 meters. All right, so we answered the question, but don't stop there. You can't stop there because maybe you made a mistake. We always want to check our answer for reasonableness. And I want to say 500 meters, that's approximately 500 yards. That's pretty tall. 500 yards, 1,500 feet, that's 10 or 15-story building. That's pretty high. So I might wonder if I made a mistake somewhere. Although, looking at this number, remember how I said earlier that this seemed pretty long for the burn phase? I suspect that this really is long. I suspect that was longer than is usual, which would mean this is higher than usual. So it's within the realm of reason. If I'd gotten 2 kilometers, 2,000 meters, I know it would be wrong. So if I'd gotten 5 meters, I know it would be wrong. So before you stop and move on to the next problem, always check your answer for reasonableness. And you may want to check it for the units too, because if you got your units wrong somewhere, you forgot a squared, something like that, your units won't work out. In this case, the units did work out because I was left with a meters on top. The units look good, the number looks good. We answered the question. I think we got it.